So one of the reasons we care about ideal gases is because as a fairly basic system, it's pretty easy to illustrate some of the more fundamental thermodynamic issues by thinking about how they work with an ideal gas. And so what we're going to do next is talk about some basic thermodynamic processes in the specific context of working with an ideal gas. Now these processes are obviously can be used with other systems besides ideal gases. But we'll use the ideal gas, our ideal gas system, sort of as to give these processes some context. So one way to think about this is that if we were interested in determining the pressure, the volume, and the temperature in a particular state for a given amount of an ideal gas. And so what that given amount of ideal gas means is that we're going to keep the number of moles of the gas constant. Well, the simplest way to do this is if you know two of those three things, and you know how much stuff you have, then you can simply use the ideal gas law. So the ideal gas law is valid for any state, state A, state B, any state in between. Right? The ideal gas law is valid at any state that your gas is in. Now, if we hold in constant, then that means that since R is the ideal gas constant, these two terms are constant. And so if I divide the T over to the other side, that means that the ratio of PV over T also must be constant. So again, now this can be, as I go from one state to another, this ratio of PV over T, that always has to give me the same value. And again, this does not depend on the process that I take to go from A to B. But what we'll see is there are some special processes that I can use which will simplify this equation. So this approach is always valid as long as N is constant with our ideal gas. If, however, I choose to go through a particular process known as an isobaric process. Isobaric is our way of saying a process at constant pressure. So on our PV diagram, at constant pressure just simply means that we're moving horizontally. So we're keeping our pressure value the same, pressure's on our vertical axis, so that means I'm moving horizontally within the PV diagram. So here I have an isobaric process from state A to state B. And since the pressure is constant, the pressure of A and the pressure of B are the same value, that means when I look at this ratio, pressure cancels out. So if I happen to have an isobaric process, so for a constant pressure process, my ratio simplifies, and what I now know is that the ratio of volume to temperature has got to be the same at states along my isobaric process. The second special process we can talk about is isochoric process. Isochoric is just another way of saying constant volume. And so if I'm holding the volume constant, since the volume is on my horizontal axis, to move from state A to state B with a constant volume process means that I have to now move vertically. And so here I'm going from state A and dropping straight down on my PV diagram to state B. Well, again, the volume of A and the volume of B are the same if this is a constant volume process. And so the volumes now cancel out, and I'm left with the ratio of pressure to temperature that has to be constant. The third special process I can talk about is what's known as an isothermal process. So isothermal tells me I'm at constant temperature. And so what you'll notice is on a PV diagram, constant temperature process is not a straight line. It happens to be this curve. It works out that this curve basically is just a 1 over x curve. But that's an isotherm in dealing with an ideal gas. So this is going from state A to state B with a constant temperature. So here I'm holding the temperature constant as I move from state A to state B. That's an isothermal process. Well, again, if the temperature is the same in going from state A to state B along my isothermal process, then the temperature cancels out. And so for an isothermal process, I see that the pressure times the volume, that product has to stay constant. The last special process we can talk about is what's known as an adiabatic process. And an adiabatic process is a way of saying that no energy is transferred into or out of the system as heat. So for an adiabatic process, Q is 0. So an adiabatic process with an ideal gas, here's an adiabatic process going from state A to state B with an ideal gas on my PV diagram. Now you'll notice that the pressures are different, the volumes are different, the temperatures are different, so there's nothing to cancel out. So this gets me back to sort of my original works all the time equation. There's nothing to simplify in this equation if I have an adiabatic process. There is, however, an expression for an ideal gas that is applicable only along an adiabatic process. And that's PV to the gamma, that has to stay constant along an adiabatic. And gamma has a different value depending on what type of ideal gas you have. So if you have a monatomic ideal gas, so this is literally an ideal gas that's simply made up of single particles, right? Then gamma is equal to 5/3. If you have a diatomic ideal gas, so that's an ideal gas that's made up of, take those two single particles and now connect them with a stick. Right? So there's some bond that's holding those two particles together. So let's say, so O2s, right? So two oxygens that are bound together. That's a diatomic ideal gas. Right? So in that case, if you have a diatomic ideal gas, then your gamma is equal to 7/5. Now, if we come and think about what our PV diagram is trying to tell us, well, there are a couple interesting things that we should know. One is adiabats are steeper than isotherms. The dotted lines here are isotherms. So here's an isotherm at a temperature TA. Here's a second isotherm at a temperature TB. And I see that my adiabat, as my system expands from state A to state B, so it's an expansion because it's going to a larger volume. So as my system expands from state A to state B adiabatically, that process is steeper on my PV diagram than the isotherm. So one of the things that we'll want to be able to do is recognize or differentiate between isotherms and adiabats on our PV diagram, and the adiabats will always be the steeper curve. And the second thing that we need to know is that in terms of looking at our PV diagram, the temperature increases as we move up and to the right. So our temperature increases up and to the right. So here's cooler temperatures over here, warmer temperatures over there. So what this tells us is that the temperature at A, or the temperature along this particular isobat, the temperature along this particular isotherm is greater than the temperature along my second isotherm. So the temperature TA is greater than the temperature TB. Which means that as my gas proceeds from state A to state B adiabatically, right, so along this adiabatic expansion, as it expands, goes to a larger volume, it's going to drop in pressure and it's going to drop in temperature. So this is a process known as adiabatic. So my adiabatic expansion results in my final state having a lower temperature than where it started. So it will expand and cool along an adiabatic expansion. And so one of the things that we'll want to get very good at is thinking about how these special processes matter in terms of changing the temperature, changing the pressure, changing the volume as I go between two states.